Hi everyone, it's Tammy Sherrow, and this is the third lecture in the series of the 3 quant lectures, and this is a short little one on what we call type 1 and type 2 errors. So errors that can occur in hypothesis testing. So let's get started. So a type 1 error, when this happens, the researcher states that a difference exists when it really doesn't. Sometimes termed a false positive. So in this case, the null hypothesis, which says there is no difference, is rejected when it's actually correct. So we state that there is a difference between groups when there really isn't one. So the probability of making one of these errors, a type 1 error, is called alpha. And alpha is that a level of significance that the researcher set for the hypothesis test. So if you recall, typically we set that at a minimum of 0.05, might be 0.01 if we want to have very, 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 very little chance that the outcome was due to chance and not the treatment or intervention, as in testing drugs. So how does the researcher go about preventing type 1 errors? And to lower this risk, the researchers must choose a lower value for alpha. However, if we choose a lower value, such as 0.01, that means that the researchers will be less likely to detect a true difference if one really exists. So envision this situation where the researcher sets the alpha at 0.01 and the p-value comes in at 0.03, which would mean they would accept the null and wouldn't detect a difference. But they decide after the results come in to readjust their alpha to 0.05 so that they can find statistically significant results. Now that would be unethical. Does it happen? Possibly. But what we look for is that the researcher does state the alpha up front before they do their calculations, and this is their attempt to prevent a type 1 error. And when we come together as a group, we're going to look at the Stress in Nursing Student article, and did they set an alpha beforehand? And then of course we'll look at their p-values and determine what was truly statistically significant. So a type 2 error is when the researcher states there isn't a difference when one exists. So opposite of type 1, it's called a false negative. And so the null hypothesis is actually retained or kept when it is false. So we state there is no difference in groups when there really is one. We really did find a statistically significant difference. So the probability of making a type 2 error is called beta. And beta is the level of power the researchers have set for the test. So what is power? Well, power is the ability of a test to detect a difference when one actually exists. And the biggest predictor of power is sample size. So power, typically your power or your ability to detect a difference when one actually exists increases as sample size increases. So we usually set the power at 0.8. That's kind of like the standard. And that is where there's an 80% chance of finding a difference when there actually is one. So how do researchers prevent type 2 errors? It depends on a number of factors we collectively call power, and we're going to look at those factors in the next slide. So there's a number of different things that contribute to power, and of course one of them is sample size. So the question we always ask ourselves is, did the researchers do a power calculation before they start to gather their data to determine and to protect against type 2 errors. So researchers have more power to detect an effect in a population if they set a larger, less stringent alpha level, so 0.05 rather than 0.01. The effect size in the population is larger rather than small. So, when we're trying to detect a difference, sometimes researchers will set what we call the effect size, so small, medium, or large effect size. And so, for example, if a drug has a large effect on a disease, it's going to be much easier to detect than a drug that has a very, very small effect. So, think about going into a dark room with a flashlight and trying to find a pair of diamond earrings versus an elephant. It's going to be way easier to detect a difference if the effect is larger. Another one is the sample size is large rather than small. So large sample sizes are able to detect smaller effects, whereas a small sample size, small samples are more able to detect large effects. And so of all of this list of things, sample size is probably the biggest. And that's typically what you will see a researcher report in their article, that they did a power calculation, they set it for 80%, and that told them that their sample size needed to be X. Another thing, researchers have more power if the data they're collecting has lower levels of unsystematic variability. So what does that mean? So the data they're collecting has lower levels of risk for measurement error, lower risk for individual differences between participants. And this is why we try to conduct randomized controlled trials in very, very controlled environments to avoid this. And we're going to look at something called internal validity, like all the different things we can do to control variation and variability in the collection of the data. And the last one is they use the appropriate statistical test. So some tests make it more difficult to find results, and there are specific tests we reach for based on what the researcher is trying to determine. So just a little graphic again. More power means less risk of a type 2 error. So if you want to think of it mostly in relation to sample size, you can see on the left side, power, more people, more power. Type 2 error states there is no difference when there actually is one. And so typically if we're looking at a study and we note that they did not find statistically significant difference between control groups and intervention groups, one of the first things we think of is a type 2 error. Did they have enough of a sample? The other thing that we sometimes need to think about is they might have set their sample size at the beginning of the study, but maybe due to other factors, they had a loss of their sample over the course of the study. Some things you study, you might lose people to death or mortality. Sometimes when you study, you lose people, you lose contact with people, you lose follow-up to people. Sometimes in a study, people decide to withdraw. They don't want to be involved anymore. And so it's really important the researcher states, what they set their sample size at and then what it ended up being. And if they don't have statistically significant results, once again, one of the first questions we ask ourselves is, could it be related to loss of sample size? So here's a little chart for you to think about and to fill in. So you're looking at possible decisions researchers make in quantitative research, and we're looking at filling this chart out to decide, what is the right decision and what is the wrong decision. So I'm just going to flip to the next slide. You could pause it here and try and fill this out on your own, and then double check your answers on the next slide. So in this situation, we've got a situation where the null hypothesis is true and no relationship exists, but we reject the null, that being a type 1 error. The correct decision would have been to accept the null. When the null hypothesis is false and we have determined that a relationship actually exists and it's due to the intervention, it's not due to chance, the right decision is to reject the null and accept. And if we accept the null, that would be considered a type 2 error. And it's once again type 2 error determined by beta or power, usually set at 0.8 or 80%. Type 1 error is determined by the alpha, or the level of significance set before the study starts, 0.05 or 5%. So here we have just a little bit of a review. We have our study findings. We're going to work down the left side first. Statistical test result is significant. P is less than 0.05. The null hypothesis is rejected. The hypothesis is accepted. This does lay out the risk of a type 1 error, but we've prevented that by setting the alpha beforehand at 0.05. On the right-hand side, here we have a statistical test result is not significant. P is greater than 0.05. So the null hypothesis is retained and the hypothesis is rejected. Here we have that risk of a type 2 error, but we prevent that by calculating the power to be 80% or 0.8 ahead of time. So power analysis and calculation. Power analysis is an important aspect of experimental design, and it really allows us, as I previously stated, to determine the sample size required to detect an effect of a given size with a given degree of confidence. And so lots of different things, as I previously mentioned, affect power, and we use computers to do this calculation for us. So a little learning check. Here is a good point to pause the PowerPoint and to try and answer the questions, and then to follow up with the answers on the next slide. So hopefully we met our objectives for all 3 lectures. Thumbs up or thumbs down. Take care. Thanks for listening.